welcome everyone. Restart. We are back after a short break with a new edition of our PowTech Technofarm virtual talk series. And I'm delighted that you are joining us to expand your knowledge of powder, granule, and bulk solids technologies, as well as liquid handling and processing. Today, our focus is on battery materials, current trends, and the impact on production. This is an important part of PowTech Technofarm. And to sweeten the way until the next event on 23 to 25 of September in 2025 in Nuremberg, so save the date, we are already bringing together numerous experts from a wide range of industries for an exchange of ideas on process technology. Experts will be on hand today to show us the latest developments. And before we go into this topic, I would like to thank our speakers, Dr. Kai Christian Möller from Fraunhofer Allianz Batterien, Mr. Andreas Kühn from Ebro Armaturen Gebrüder Bröhr GmbH, and Dr. Jürgen Adolf from Microtrack Bridge, without whom this would not be possible. And now I hand over to Dr. Kai Christian Möller from Fraunhofer Allianz Batterien and his talk about current trends in battery technology. So enjoy the talk.
Okay, thanks Marianne for the kind introduction. I now will give a short introduction on lithium-ion battery technology and on the current trends we have in the battery technology in general. First of all, a short glance at the Fraunhofer Gesellschaft. It's sometimes a little bit complicated to understand what we are doing. We are a very large society for applied research, and we are about 30,800 employees, but we are divided over whole Germany in 76 institutes. We have a research budget which has a third approximately base funding from the federal and state governments, but this is something like the unique selling point. 70% we are working in projects directly with companies or in publicly funded research projects. For the topic of batteries, 26 of our institutes are working in the battery value chain. You can see the institutes here with a small icon, what they are doing. We start with material research. We make cells and cell production. Even we are building up a small gigafactory for cell production in Münster. We are dealing with systems and integration, means battery management systems, thermal management, end of battery life and battery recycling. All is accompanied by simulation and modeling and testing and evaluation of materials and full batteries. So far, the lithium-ion cell consists of two electrodes, the separator and the electrolytes. That's the very easy version. The anode has a current collector made of copper with the active material on it. The same as with a cathode, an aluminum current collector with the active material for the cathode. Then we have a separator and everything is soaked with electrolyte. So in the end, you have a battery like this, where you have the sheets alternating cathode, anode, and the separator to prevent the short circuit. The composition of a typical cell you can see here. This blue amount is the 40% cathode active material. The anode contributes with 20% active material. In these two components, you find the energy density, the energy storage is in anode and cathode. And all the other components you need, but they dilute somehow the energy density. So you need electrolyte, you need the current collectors, copper and aluminum foil, and also the binder and carbon black as conductive additive and the packaging and so on. This is a general approximation. The exact amounts depend if you have a high energy or a high power cell, but this is more or less the amount for a high energy cell. These lithium-ion batteries are expected to reach their limit at around 350 watt-hours per kilogram in the high energy version. If we have a closer look at the materials, we have here the graphite, which is the state-of-the-art material for the anode. But in future, we expect the use of metallic lithium. You know, lithium batteries, which are non-rechargeable as primary application, button cells for your remote controls and so on. And in future, we see increasing amounts of silicon, which has a higher capacity for lithium storage. And maybe more a niche market, the lithium titanate. This is an oxidic material with very high power capabilities, but the energy storage is not so good. If we have a look at the different morphology of the electrode materials, we have the state-of-the-art graphite powder, not in flakes as you would expect, but it's with high effort formed to so-called microbeads. You see the diameter is approximately 10 to 15 micrometers to make high-density electrodes. These materials are mixed with conductive additive and binder, and they are mixed with a solvent to get the slurry, and this liquid slurry is coated onto the current collectors. A little bit different looks the lithium titanate. It's a nanomaterial. It's in the electrochemical stability window of the electrolyte. So it has a high surface area and small particle diameters. This means the diffusion of the lithium ions in the particle and out is very short, and the battery can react very fast and give high power. A little bit different compared to the carbon. In future, maybe we will see lithium, presumably in lithium sulfur cells for some flight applications, flight taxi, or for solid state batteries. This is completely different. This is a sticky, soft metal foil, which has to be put into the cells. And what is done at the moment already in small amounts is the silicon carbon composites. You can see here the graphite flake, and the white shadows here is the nanosilicon. Silicon can store large amounts of lithium, but the volume expansion is approximately 300%. And this has to be handled in the electrode. It's also possible to use pure silicon, but the technology is a little bit different. It's a vacuum deposition of silicon on a structured copper foil, and these columns, let's say, breathe and make the battery electrode thicker and thinner during uptake and release of the lithium ions. It's not so easy to incorporate silicon into the batteries. You can imagine the volume expansions are very difficult to handle. And one example you can see here, where you have here the cycle number and here the electrode capacity. If you just mix the silicon and the graphite, the decrease in capacity is quite strong, especially in the beginning of the cycle life. And value would be a remaining capacity of 80%. This will be reached at already 20 cycles, which is not good enough for an application. But if you have an optimized material and have the nanosilicon somehow incorporated into the graphitic structure, the values are much better for the remaining capacity. So you can already reach 150 cycles, which is quite good, but not enough. A rule of thumb would be to have after 500 cycles, also somewhere here, remaining capacity of 80%. So there is still an effort to do. The summary of the anode materials is seen here. The specific charge should be as high as possible. You find here the metallic lithium and also the silicon, which would be favored electrode materials for the future. And the voltage here should be as low as possible to give high voltages to the cathode materials. This is a market overview. Looks a little bit simple because most of the material is natural or artificial graphite, little bit amorphous carbon, and the silicon mixtures increasing in the next 10 years. Let's switch to the cathode materials. There we have oxides, metal oxides or phosphates with a high oxidation state to give high voltages. So we have layered structures, spinels with 3D structures, and the so-called olivines such as LFP, lithium iron phosphate, with linear lithium chains. These are the prototypes of the structures, but there are many other layered structures. Maybe you have heard from NCM materials. The driver is to replace the expensive cobalt and reduce it to 1/3 or even to only 10%. And this is, let's say, a material up to date with 80% nickel, 10% cobalt, and 10% manganese, abbreviated to NCM 811. This is very similar to the NCA, the lithium nickel cobalt aluminum oxide, which is made by Panasonic for Tesla. And for the future, we have lithium and manganese rich NCMs. You see here there is more lithium inside and the specific capacity would be higher. For the spinels, we have the possibility to go to higher voltages, as shown here with the high voltage spinel. And with the olivines, they don't have such a high voltage, so it's more or less a lower capacity in the batteries. But this can be improved by the addition of a manganese to the so-called LFMP material. All these can be seen here, where we have the specific charge here. The high energy NCM gives the best specific charge, and the best voltage would be the high voltage spinel. If we have a look at the market, we can see here the increase in the NMC materials and even much stronger, the increase of the lithium iron phosphate LFP, which becomes more and more dominant, starting in China in lower range and lower budget cars, and especially in buses. So far, the lithium-ion technology with improvements in active materials. The next trends I would like to mention are the sodium-ion batteries and solid-state batteries. The sodium-ion batteries are quite similar to lithium-ion batteries. We use carbon on the negative electrode and different metal compounds on the positive electrodes as Prussian white, or also layered oxides such as the sodium, copper, iron, manganese oxides, layered structures as we already know from the lithium-ion battery, or different compounds such as sodium superionic conductors, abbreviated to NaSiCon. These batteries have a lower specific energy. We expect around 160 to maximum of 200 watt-hours per kilogram as announced by CATL. The advantage of this technology would be it's using sodium. It's a common and inexpensive raw material from available resources. You can use on both electrode sides aluminium instead of copper, and the production should be quite similar to lithium-ion batteries, so you call it a drop-in technology. You can presumably use the same equipment for the production of the electrode and the cells. And it's somehow on the threshold of commercialization in the first examples for electric vehicles. More information you can find in studies from our Fraunhofer Institute for Innovation Research with this QR code. You find a study on the sodium-ion batteries worldwide and roadmaps and predictions. And let's have a small look at the lithium solid-state batteries. They should be, if you have a look in the newspapers, on the road again since 10 years, but unfortunately it's quite difficult to commercialize this technology. Toyota announced 2011, so 13 years ago, to have this commercialized 2015, 2020. But they updated it last year, so the new launch should be 2027. And it's very difficult to scale up from laboratory scale to large scale, this technology. And so far, the only car with or only vehicle, let's say, with a real solid state battery would be this kickboard from Toyota. What are the advantages of this technology? First of all, you have a non-flammable, non-liquid electrolyte. So the safety of the cells is better, and because you don't have a porous separator, you have a solid, it should be possible to use a lithium metal anode, which is much thinner than the carbon anode active material electrode for the lithium-ion battery shown here on the top. So the energy density is the key driver for the cells, and the safety, and maybe some other smaller advantages. The Solid electrolytes are already existing. The difficulties are to incorporate them into the cells. That's not 100% true. Let's say easier version would be to use polymer electrolytes. They have advantages such as mechanically flexible, they are easy to process, but the disadvantages are that they are not stable with high voltages, and that these batteries need approximately 80 degrees C in the car. Then you can use real metal oxides or sulfates. They have a good ionic conductivity, but they are not stable in air and difficult to process. And then there are oxidic ionic conductors. They are stable in air. They are already oxidized, but they are very brittle and difficult to process. And to make the electrodes, you need sintering at high temperatures. And one of these electrodes you can see here in this electron microscope picture. You see the particles of the active material and the electrolyte in green. It's a big difficulty to make these compounds with a good contact. If you imagine this active material particles increase a little bit in volume if they take the lithium inside, and if they release it, they shrink a little bit. So the contact for electrons and lithium ions is somehow hindered. So we have still a lot of hurdles and challenges for this technology. A detailed view you can find in this study from our Fraunhofer Institute. You can get the PDF for free with this QR code. So I hope I could give you a short overview on the lithium-ion technology and the future technologies, sodium-ion and lithium-based solid-state technology. Thanks for your attention.
Thank you very much for this interesting talk. So now, if you have any questions, please write your questions in the F&A button, and then I will hand it over to Ms. Möller. So now one question. What are the biggest challenges in the production of classic lithium-ion batteries?
I would say it's the electrode production. So there you have many parameters. You have the active materials, which can be moisture sensitive. You have the current, the carbon black, you have the binder materials, and you have the solvent to make the slurries. And the switch is to get from organic toxic solvents to water, which is not possible with all cathode materials because they can leach out the lithium and will not work as expected. And then you have to coat the slurry very exactly on the metal foil with a thickness. You have a drying process after the coating, which takes a long time and a lot of energy to dry the electrode and recycle the solvent again.
Thanks for your answer. One question is also in the F&A button, and it's, is the particle size and structure for graphite and lithium titanate a limiting factor for the battery performance?
Yes, exactly. The graphite has to take up the lithium ions, and these diffusion processes have limits. If the currents are too high and the temperature too low, the lithium ions cannot go so fast into the graphite structure because they have to fill up these layers, these graphene layers. So you have something like a traffic jam in front of the graphite particles and a lithium metal deposition, which can form dendrites and give short circuits. This problems you don't have with lithium titanate. This material you can use as nano material with very small diffusion length in the particles. And you have, let's say, safety to the lithium metal deposition of 1.5 volt, which means in the same, the energy density of this material is not so high because you lose 1.5 of this voltage. So this is more for high power batteries.
Thank you. I think we can answer one question again. So, on what time scale do you think the challenges of the solid state battery can be solved?
That's a difficult question. Toyota tried it 13 years ago and they were wrong. At the moment, I see increasing research all over the world and very focused research and announcements of solid state batteries everywhere. So I guess in the next 5 years, we could see the first prototype batteries, first prototype cars. But the lithium-ion batteries are becoming better and better. So the advantage of a solid-state battery has to be proved still, because then in 5 to 10 years, the solid-state batteries have to compete with better lithium-ion batteries, which are at the moment much easier to produce. We will see.
Thank you. So, one other question, how the development of lithium-free batteries can be speed up?
Lithium-free batteries. This would mean sodium batteries, I guess. Efforts in research, I would say. Commitment of companies who develop anode and cathode materials. I guess this is a crucial thing because the production processes are expected to be similar, but the material research is at the beginning. So the research efforts for this would be most important.
Perfect. So one last question, I think. So what energy densities are realistically expected for solid state batteries?
Maybe 400, 500 watt-hours per kilogram compared to 350 for lithium-ion batteries. 300 is already real. With increasing amounts of silicon, this can be 350, maybe a little bit more. And the lithium-based solid-state battery, in fact, doesn't need an anode because the lithium is already in the cathode. So maybe 500 could be possible.
So I see we get one or two more questions and we have a little bit of time left. So I think we can answer them too. So which of the battery types presented can be recycled best?
That's difficult to say. Lead acid, I would say, because we have lead on both sides, on anode and cathode, but this I didn't present. But these batteries are present in every car still. There is still not enough knowledge on solid state or sodium-ion batteries. I expect sodium-ion batteries could be recycled as good as lithium-ion batteries. and solid-state batteries would depend on the solid electrolyte. Or solid electrolytes, if there is one for the bulk, different from the cathode electrolyte.
And then another question, how important is the pore structure inside active materials?
Very important, I would say, because these electrochemical reactions take place at the interface between electrolyte and solid phase. And the more pores you have, the more surface, the faster the material would react, and the less would be the lithium from the electrolyte depleted. So the pore structure is very important.
So then, thank you very much for your presentation and answering these questions. And now we're going on with our next talk. It's about discharging and dosing of abrasive battery raw materials under emission control and explosion protection conditions. So now I look forward to Andreas Kühn from EPRO Armaturen Gebrüder Böer. So the stage is yours.
Yeah, thank you very much for the nice introduction. I was really fascinated about what we heard before, and I would like to just seamlessly go into these technologies and how to handle these materials. So actually, we are in Schnitzel Valley, so it's 1:30, and everybody's a little bit tired. I hope I can fascinate you with some practical things here. So we are talking about valves, butterfly valves, mostly knife gate valves. We learned from the previous speaker that we are talking about mostly solid materials, and solid materials are supposed to be handled in machineries connected with piping systems, and so on. A few words about EBRO beforehand. So EBRO is a private company owned by the family Bröer. We are about 1,000 employees worldwide, and we have 28 subsidiaries, 6 production sites, just to make butterfly valves and knife gate valves and components. So here we can take a short, brief look. We have the classical shut-off valve on throttle valves. So there is the PTFE, there is the soft line, there is the metal-seated valves. We have the knife gate valves for your discharging. And we have special valves, which I would refer to, which we use in the battery production. Actually, we have the valves here for the shut-off and throttling, which are the butterfly valves, metal-seated, soft-seated, PTFE-seated. We have knife gate valves here for the process of the battery production, handling of the raw materials. And I would like to refer to special valves on the left side here, used in the handling of solid materials. So in addition to the valve itself, EBRO is producing the actuators, the pneumatic actuators, single and double acting, and the electrical actuators, and also the position feedback systems to mention, is the valve open, is it closed, is it somewhere in between? And nowadays we use IO-Link, we use Bluetooth, and this is integrated into Internet of Trusted Things. Actually, when it comes to the butterfly valves used in battery production, we have certain requirements that go a little bit beyond the standard butterfly valve. So not to contaminate, and that's one of my topics here in the containment questions, not to contaminate the product, the raw product, dry powder, lithium, zinc-free, And copper-free materials must be used not to contaminate the lithium or the graphite or the other raw materials we just saw before. So we completely refrain from copper, from zinc, and mostly we use stainless steel components here to make sure that we don't bring anything into the product stream that could influence the chargeability of the cell in the end. Of course, a lot of those products we have seen are abrasive. So it's not so easy to handle those materials without creating abrasion wear on the machinery. This is the mixer, the sieving system, the weighing containers, whatever helps to handle the material. And we still have the problem that we should not contaminate it. And of course, since the materials are not healthy every time, and we don't know what the research and development will bring up in the future, we must make sure that nothing goes into the product stream, and foremost, nothing comes out that could influence the health of the people in the vicinity or create troubles otherwise. So when we talk about battery production, we talk about a certain supply chain that starts with the mining processes. So wherever we find mining of these materials, here we have the Atacama Salt Flat in Chile. There you will find water management, and you will find a solid material management, which contains butterfly valves and knife gate valves all the time. So from the very beginning, we take care of these mining processes and further on. So it may be a wet process, it may be a dry process. You just read that big deposits of lithium have been found in Finland. And of course, the mining processes have to be as clean as possible, because everything you bring in the first step of the supply chain, it's very, very expensive to get the contamination out of the products in a later state. So we learned about the anode, the cathode, the graphite, the electrolyte, and here comes the material that gives us the most headache. So these are abrasive materials that could destroy your machinery pretty quick. And we want to make sure that the maintenance cycles are as long as possible. And that indicates that we have to take care for these things. All in all, every giving over the material into the next step of the production requires logistics. So from the mining into the factory to purify or refine the raw materials into the cell production and even into the clustering, we talk about logistics. And that includes, of course, the procurement, the production itself, the outlet, and not to forget the recycling. And everywhere where we have one of those seams here, there is the risk of contamination. There is containment necessary to make sure that nothing goes into the atmosphere and nothing from outside goes into the production process. So I would concentrate on the production side right now. This is the main thing. Could you imagine to have a ship going into a European port nowadays carrying lithium in an open vessel? So this is not possible anymore, because lithium might be even life-threatening if it comes in a certain concentration in the body. So we make sure that all the logistics is a closed process as well. It still isn't 100% worldwide, but we are working on it. That's the reason you very often find IBCs, intermediate bulk containers, who handle those materials. They are stored here, completely sealed off, so nothing goes into the atmosphere, and they can be discharged through a valve. Again, it's a butterfly valve here. I call it the tennis rack because it has a long neck and a tilted handle, not to collide with the cone of the IBC. And these valves, of course, are completely copper-free, completely zinc-free, not to contaminate anything. More difficult products, which are explosive or are carcinogen, so not so healthy, they are transported in smaller bins, completely sealed off, and you find always butterfly valves here in the discharge and charge system. In the internal processing, you find a lot of pneumatic conveying systems. So conveying means overpressure conveying. The material goes from a silo, a hopper, a big bag, or an IBC into a pneumatic conveying line. There is a compressor creating overpressure, and it is sent through pipelines. Here we have a suction system where we create a vacuum here in a separator, and the material is sucked into the next step of production. And everywhere in these processes, we find valves. Here another sample, we have a mixer. Since I had to sign a lot of non-disclosure agreements, I cannot show you makers or real pictures out of the production process, just these sketches. But everywhere we have valves to make sure that the material goes in and nothing goes out on the wrong end. And of course, we have the dust collection systems going to bring out the particles that are in the air. So in the cell production itself, we bring together the powders, which are ground or classified. Then the liquids come and we create a slurry and a paste, and it is mixed, and everywhere you find those butterfly valves, completely copper-free, completely zinc-free, and capable of bearing ATEX relevant materials, organic materials like graphite, and prevent explosions. I can use this picture, the company allowed me to. So here we have the valves sitting on the mixers where the slurry or the dry powders are mixed and concentrated. And sometimes you see strange things here. So the customer does not want to have any metal ions going into the process. And so they use plastic piping, polyethylene piping, and that gives a headache for the butterfly valve, which we can solve. Actually, to bring material from level A to level B, let's say from a silo into the mixer, you can use a lot of equipment to do that. We want to make sure that if an explosion happens in the mixer, the explosion cannot travel into the next stage above, into the silo or the bin. And we make sure that we have a passive explosion decoupling. Even during cleaning processes, we don't have to open those things. We call it cycle lock. There is no backdraft, there is full containment, nothing goes into the atmosphere at all. And it has not to be open, we can clean it in place. And there is zero emission. And the total cost of ownership and no compression. Explosion decoupling means if something happens in one part of your machinery, we will stop the explosion and not let it travel into your other machines. You can download the video on YouTube how cycle lock works. So the material sits on the upper valve. We discharge it into the spool piece. We close the upper valve and we discharge it into the next step of process. It's a video. I just have the stills here. So these things can be used as inertizing systems. So the material coming into the spool piece can be inertized by nitrogen, by replacing the air by nitrogen inside the spool piece, and we let the material go in an inertized state. Of course, everything is according to ATEX, down to the highest grades, zone 020, 121 outside, and it's a passive explosion system. If you need more information about it, I'm willing to share it with you, of course. Here's some samples out of times when NDAs not had to be signed. So this is about 7-8 years ago. Cycle locks are used to bring the material, the raw battery materials into the next step of production by using cycle locks. Of course, we want to make sure that no material out of the valve goes into the product stream. And you see these strange hoses here. That's a valve we call inflatable seat. I will refer to that. Of course, when you have a production process, dust occurs. The dust is collected in baghouses, in filters, and to discharge the material from those filtration devices, we use the cycle lock not to bring false air into the process and not to contaminate anything to the atmosphere. This is my favorite silo, of course, very tricky material. I prefer to eat cornflakes and not cornflakes dust, so we have to be very, very careful in the handling of the product, and we want to discharge it in a controlled manner. That's the reason we use something we call impeller valve. It looks a little bit like a butterfly valve, but it has a 6-blade wheel inside and a standard gear motor, so we can discharge kilo by kilo by kilo by kilo in a controlled, homogeneous manner. So, for instance, to charge the pneumatic conveying system, and we don't want to overshoot it, then we use impeller valves. Or you want to go into a weighing system or into a sieving system, then these valves are used in the battery production. Of course, everything copper-free, zinc-free, and according to ATEX. That's what I mentioned. You see these hoses again. Here's a butterfly valve that looks a little bit strange. But the main source of contamination is the wear off of the rubber. So you have to seal it off, but there is some rubber. And when the disc squeezes into the liner, into the rubber liner in the sealing, then you might scrape off some particles and those go into the product stream. We prevent that. We use a smaller disc. So when we close the disc, there is still a little gap. And then we press compressed air or nitrogen, depending on the process, and we inflate the liner. We press it against the disc edge, and we prevent the rub off when the disc is opening and closing. And so the lifetime, the lifespan of the valve increases drastically. The vibration dosing is a valve. Also, we take what we know best, a standard butterfly valve, a standard actuator, a positioner to control the opening angle and therewith the volume stream, the flow of the material. But sometimes solid materials don't flow easily when they are throttled down. So we bring in some vibration directly into the disc and make sure that the material is still running. So here's one of those systems in another application. And here you see the vibrator, and the vibrator brings the kinetic energy into the disc, and the disc vibrates and keeps the material flowing. Even with difficult materials, this is very appropriate. Of course, we can combine the inflation of the liner with the vibration, and this is the perfect valve, stainless steel, completely mirror polished for many applications in the battery production. Some samples here. So even if you close down the valve down to, let's say, 20 degrees opening angle, the vibrator makes sure that the material is still running, even if it is a very complicated material. So we just learned, we have the copper foil, we have the aluminum foil, we bring on the slurry, we dry it, we cut it off, and the battery cell is then produced and clustered. And that's the end of the line of the production. And I just want to make sure, if you are not careful in the beginning of the process, you only realize that a battery cell is not working properly, does not have the right capacity when you charge it for the first time. So not to contaminate the raw materials with things that could influence the capacity of a cell is absolutely necessary to prevent throwing away parts of your production. So make sure that the raw materials are handled properly, and then you don't have the problem to throw away already produced cells. So as I mentioned, the valves, butterfly valves, knife gate valves are in all kinds of production processes. Since we have to handle a lot of dry powders, we regard ourselves a little bit as the experts in powder handling, powder and bulk handling. And you find those valves in filtration systems, in vacuum transport, but also in water treatment, in the air dryers, in the compressors, and so on. And all of them have one thing in common: copper-free, zinc-free, and explosion protected. And we make sure that nothing goes into the atmosphere out of those pipelines. Not to forget, I use one of my favorite things here with one of our customers. We have to make sure that we recycle everything. And when I say everything, I don't mean only the battery cell at the end of the lifespan, but also the valves. The valves have to be completely capable of being disassembled and recycled 100%. We commit to that. We are on the path to the sustainability, and we make sure that this is followed in all of our production processes internally. Thank you very much. If you have questions, I'm willing to do that, and just let me know. Thank you.
Thank you very much. So now I check the F&A button. So if you have any questions, please type in this button, your question. And then I hand it over to Mr. Kühn. So I wait a second that you can type. Okay, one question. You mentioned the term explosion decoupling. What would be the safety standard, and have you got a type approval document by a notified body?
Oh yeah, that's the good question, because this took a lot of research and development and of course money to achieve that. Those cycle locks, which are supposed to hold up explosions, they are type approved by DEKRA down to a performance level D, which is uses valves similar to SIL, SIL 2. And this is capable of bearing explosions up to 10 bars. And we can use those in dust class 3, which would be aluminum dust and things like that. So that's a good question. Thank you very much for it. Yeah, we have the type approval, and it's necessary to keep you free of any trouble. So you just can point to the document you receive from our side.
Thank you. Another question. Have you seen the transportation of AAM and CAM in IBCs in an industrial scale on an international level?
It's a big tricky question, because I'm bound to non-disclosure agreements. I can refer to that in a private conversation. Maybe you get my email address and you contact me. But I have to be careful what to mention here and what not, because there is a lot of money involved with all the makers of battery cells, and they don't want to have all the information going in the whole world. So I'm sorry I cannot answer it here, but I can give you some hints in a private conversation.
So another question, do you have experience on vacuum applications, talking about the tightness of valves vacuum against atmosphere?
Yes, definitely. So the experience comes from other parts, not only from the battery production, but also from high vacuum applications. And we did a lot of things to make sure that we can handle this, but it depends always on the process. If somebody says, yeah, it's all no problem, no sweat, we can do it easily. No, every case is different. And let's talk. that's the main thing. Just explain your application and we will find out what can be done. And we are in this business for a long time. If it is not possible, we will tell you. And you can search for other applications. But that's an open-minded discussion. But we have to talk about it.
Perfect. And again, another question. Do you have any wear protection for the flaps, such as alumina ceramic coating for the discs?
Yes, it is possible. We use tungsten carbide coating. Sometimes Hardox is sufficient. It depends on the material and the application. We can coat the disc. This is one point. But we often use deflectors. I couldn't refer to this here in this presentation, to protect the disc edge that's pointing into the upstream. So there are possibilities to protect the disc in it. And of course, the inflatable seat takes out the liner out of the product stream to make sure that the abrasion on the liner is as low as possible. We cannot bring it to zero. Everybody who says there is no emission, there is no wear, no tear at all, I would doubt that, but we can do a lot to meet those requirements.
So another question, you have mentioned copper and zinc-free execution of your valves. Are they also free of aluminium?
Yes.
Sorry.
Yes, it is. Yeah.
Yeah, and it's the same in the same questions. Another question, does zinc-free also mean zinc-free paint on the valves outsides?
Yes, the best is you don't use paint at all. So use the stainless steel body, which is SS316 14408. That's the best to do. And don't forget, in some aluminum alloys, there might be up to 5% of copper. Some people don't realize that. Some alloys contain a lot of copper. So don't use aluminum only in case you have no other chance. Otherwise, we have fantastic stainless steel bodies that can handle the problem easily.
So another question about wear protected valves. Is wear protection also possible for the explosion decalping valves which have type approval?
Yes. So we have the type approval for all of, or most of our butterfly valves and the knife gate valves as well. And that's, yeah, that's type approval by DEKRA. And again, if you need details, please contact me. I will send it to you and we can discuss it.
So I would say one last question, in which applications are those systems already implemented, and could you provide references?
Oh, that's difficult. Of course we can. So in the raw material handling, in the beginning of that chain, there are no or very few non-disclosure agreements. In the final processing, there are, so I cannot mention references here online, That's not possible, mostly not possible, but there is a lot of applications in this field. Wherever you go, from northern Canada to Australia, where these valves are used. So if you're interested in containment questions to be answered, which I could not do here in the 20 minutes, we have a containment meeting on the DSEV, which is the Deutsche Schüttgutindustrieverband, on the 20th of June in Hagen in our facility. So there is a chance to go into the discussion face to face, and we can explain further details about it.
Perfect. I see 2 questions are coming in now, so let's take the time and answer also these questions. So what are the temperature limits on vacuum-tight valve systems?
Soft-seated, we are limited to 180 degrees Celsius in total. It depends a little bit on how much powder could stick to the disc. And in the high temperature range, we go up to 400 degrees Celsius. But this has some disadvantages. A metal-seated valve has always the risk that powder can get stuck on the sealing surface. So we have to make sure that we use those deflectors, not to get any particles sitting on the disc edge when it closes into the metal seat of the system. PTFE valves can be used up to 220 degrees Celsius, but they are of course subject to tear and wear. So it depends on the product. So with graphite, no problem. With other materials which are sharp edged and abrasive, there might be problems. Let's talk about it.
And now the last question, because the time's running out. Which wear protection do you use for transport of these abrasive materials? Stainless steel housing is a must.
Yeah, stainless steel housing is a must. I agree to that. Of course, there are processes where it is not absolutely necessary. So it depends on the process, of course. Yeah, so we make sure that we use coated disc. So there is some different coating systems. We can use duplex discs, which are much better than the usual stainless steel discs, but we can use all kinds of materials for the discs as long as it is weldable.
So thank you very much, Mr. Andreas Kühn. And now we hand over to our next talk. Last but not least, I will hand over to Dr. Jürgen Adolphs from Microtrack Retsch and his talk on particle and pore size characterization of battery materials. The stage is yours, Mr. Adolphs.
Okay. Hello together. Can you see the screen?
Yes, we see the screen and you can start the presentation.
All right. Okay.
Perfect.
Yeah, great. Well, thank you very much for the invitation. I will speak about particle and pore size characterization without having met Dr. Möller before. So we met actually first time here, but maybe we can get some insight in these topics. So batteries are everywhere, and it's of course a huge market. We think about maybe which will reach in the vehicle battery market more than $80 billion in 2026. It's found in vehicles, cars, all kind of also medical applications and so on. So the improvements in battery costs and performance is an older report from 2018, but it's still valid, I would say, because the costs of batteries should be reduced remarkably from about $130 per kilowatt hour per cell to down to about 50 in 2035. The density should be doubled at the same time. Power density by factor 4. Of course, safety is an issue, recyclability, temperature, and first life issues. So the battery, we have seen already some slides. It's how does it work? How do we make such kind of battery? Here's an example for a lithium-ion battery. So we do have some raw materials, graphite powder, electrode foil, for example. It's very simple picture, but it may give you a rough idea of what's going on. So we do the electrode manufacturing. That means we do have the copper foil. For example, we have a slurry. We coat this slurry, then we apply pressure and heat in the calendering process. And finally, it's cutted and slit, and then we do the cell assembly. A lithium battery is in action is shown here. We have a discharge. So when you charge it, then we will see the opposite directions for the current and the electrons. But we do have here the cathode. We have a separator, and we do have an anode, and the whole game plays between these two, and it's like a volleyball game, maybe with a net, the separator in between. Okay, who are we? We are part of the Werder Group. Werder is a privately owned company by Andres Werder in the second generation, and meanwhile we call ourselves Microtrek. Before we had Microtrek MRB, but we're getting more and more companies in our company within the Werder Group. So we are dealing with particle size, and actually we were the first in with Microtrek for dynamic light scattering in and the laser diffraction particularly. Our location is in for manufacturing in the USA. This particle size and shape measurement equipment is produced here in Hahn, and I'm sitting right now over here in the window. So surface area and porosity measurements equipment is made in Osaka in Japan, and porosimetry, pyranometry I brought with my former company also 3 years ago, Porotech, to the Werder Group. So this is a picture of the site in Osaka, and last year we acquired also Formulaction. So this is a part for the dispersion technology sitting in Toulouse in France. I will come now to a first part for the particle size characterization, and in combination with a laser diffraction device and a dynamic image analysis. So we can cover particle sizes from about 0.01 micrometer up to 4 millimeter with these devices. We can do these measurements in a wet dispersion or in a dry dispersion. These are also working according to these ISO standards for laser diffraction, as well as for the dynamic image analysis, and of course for the representing of the results of the both. The view inside of such a device, you see here the up to 3 lasers, laser 1, 2, and third laser, and an array of detectors. Detector 1, which is on axis between the laser 1, for example, and the detector 2 for off axis. We have here the sample cell. So these are the docking stations we can choose. I will not show the image, the video right now, but what is important, we do have here a camera. So we can measure the particle size by the laser diffraction technique, but we can also see particles. And this is shown here for a synthetic graphite, for example. Only the laser diffraction gives a particle size around 10 microns. And with the dynamic image analysis, the DIA, we see some oversized particles, and you can see them here also in the pictures, 131 microns, so quite lengthy particles, 114. All these are above the optimum size for that case of 10 microns. And they will disturb the performance later on. So it's good to know these particle oversize in the production, for example, of your graphite for your electrodes. Since there's another thing to remember, the statistics for laser diffractions are very high, and for this reason, you will not be able to determine the few of these oversized particles, but with less good statistics of the dynamic image analysis, you can see this, and then we can add here. Another example is for a milled coke. We have only the laser diffraction in the upper part around 10 microns. And again, with the dynamic image analysis, we see then particle size also over the 100 microns. They are also shown in these pictures here. Another system, a pure dynamic image analysis machine, is the ChemSizer series. So in the series, we can work depending on the equipment, determine particle sizes in the range from 0.8 micrometers up to 135 millimeters. The latest innovation, we had a patented 3D measurement technique where particles flow, for example, over a vibratory feeder and then fall down, and along the trajectory with the camera, we can see and follow all the various movements of the particles and then get an idea also of their three-dimensional morphologies. The example I will show you here is a ChemSizer X2 experiment on metal powders. So the particle size you can determine with the ChemSizer X2 are in the range of 0.8 micrometers up to 8 millimeters. And from image analysis, you can get different information. So one is, for example, the minimum width of a particle, which is best suited for sieve correlations, for example. Or you can calculate the area, which is then the same as related to a diameter, which is the same area of a circle or a spherical particle. Or we do have a ferrite diameter, over it, which is actually, in this case, it's the maximum diameter over the entire length, for example. And we have two different materials, two different metals here. One is a copper powder, a fine one, and a so-called coarse one. The red one is the fine one, orange one is the coarse one, and also a silver powder as a fine, which is in green, and the coarse in blue. And when we do the measurements and the particle size distribution according the minimum, the width, again, this is something you will get also when you do sieving as a value. We see that the D10, D50, or D90 values of all these metals, almost independent of their coarseness or fineness, are more or less in the similar range. So the coarse copper and also from the laser diffraction is a comparison here between the coarse copper and fine copper are almost the same particle size. However, in reality, they have a different morphology. So we see here on the left-hand side, silver looks very crunchy, and the copper looks like very nicely spherical particles. And we can, from these shape forms, define different values like an aspect ratio, like the circularity, symmetry, convexity, compactness, which is shown here on this side. And again, we see now a much bigger difference when we use, for example, the aspect ratio between as a measure or to define the particle, to characterize the particle between the silver, which is here much higher, less than 1. 1 would be a perfect sphere, compared to the copper, which is approaching the value of 1. Or when we look for the compactness, we also see differences between the silver, for example, here, and the copper. So when we do have particles, they have the same size, same shape. We will not, but they are non-porous on one hand, like on the left-hand side, or a porous particle like on the right-hand side. you will not see a difference in these kind of data, for example, for particle size analysis. But the behavior and the properties are very different, like the porosity, the surface area, moisture uptake, catalytic properties, friction, processing, and so on. And this is now the next step, that we will investigate and characterize porous particles. The name says already porous, so we are interested in the pores of these particles. Pores are determined by the pore size per volume. And of course, they also will offer a much higher surface area compared to a non-porous particle. One of the techniques we use is the so-called gas adsorption technique, or resorption technique. What we do is we are working at a constant temperature, typically at cryogenic temperatures. For gas sorption, we take nitrogen at the gas, and for example, and keep it at liquid nitrogen temperature, which is 77 Kelvin or minus 196 degrees Celsius. And in the equipment, I will show you shortly later, we apply first a vacuum. That means we have here a scheme of a porous particle, then the surface is free at vacuum conditions. And then we start to introduce stepwise amount of nitrogen gas, for example. Micropores will be filled, monolayer may be formed over on the pore walls, and at higher relative pressures with more introduced amount of nitrogen molecules, we may also have a capillary condensation in the pores, and then at the end, at the saturation pressure, a filling of all the pores. So there are two regions, more or less, which are mostly interesting. This is the region of the formation of the monolayer, because from there we can calculate the specific surface area. That means the surface area as a function of the mass, of the dry mass of our sample, according to the Brunauer-Emmett-Teller theory, for example. And another region is quite often very interesting. This is the pores, so the micropore or the mesopores, where we are interested in the pore size and in the pore volume. So this is typically done with so-called BJH theory, the Barrett-Joyner-Hollander. So the equipment we use is shown here for applications for very fast surface area measurements. So we can do this meanwhile in the range of about 20 minutes. For 4 samples, for example, we use the Belsop Mini X. It's equipped with a rotary vacuum pump, while the systems Max G, Max X use much better vacuum. So they are equipped with turbomolecular pumps and then also dedicated pressure transducers working in the pressure range down to 0.1 torr, for example, where we can also determine then the micropores. So now I'm coming to an application, to an example of a lithium sulfur solid electrolyte, which is synthesized in 2 ways. One is in the liquid phase and one was produced in the solid phase. And you see here 2 scanning electron microscope pictures from these 2 electrolytes. So the problem is that these must be protected against air, in particular when we want to know pore size and surface area. And usually we handle our samples in air first and then do evacuation, but from the production, it needs to be protected already against air. So there are two ways. Either we use special sample cells, which is shortly shown here, where we can put in our samples under protection atmosphere, maybe in the glove box, into our sample, seal them, and then put them in our machine for the measurement. Or since the Belsop Mini X is a very small instrument, only 28 centimeter in width, 65 in the height, and 47 roughly in the depth, we can place it also in the glove box. So now the measurements shown here. So the isotherm, this is the adsorbed amount we find here for the 2, and this is the relative pressure. Then we see here the solid phase. This is one on the right-hand side, you see, and this is the isotherm of the electrolyte made from the liquid phase. And we see also a difference in the pore size here in the BGH plot. And the surface areas also are quite different, what you could already maybe guess from the electron microscope pictures. So we get here BET surface area of 3 square meter per gram for this electrolyte made from the solid phase, and around 20 square meter per gram from this one made from the liquid phase. So this is a machine where we can determine surface areas and pore sizes in the range up to about 100 nanometers. Another interesting feature or information is the density of electrode material, for example, and this can be done with a pycnometer. You can place your pycnometer into your pycnometer your powders. In our systems, like the Bell PycnoL system, we working from the reference chamber by introducing about 2 bar of pressure, then releasing it to the sample chamber and then we, from the pressure differences, we can then measure the amount of powder, and by the mass, we then know the density in gram per cubic centimeter, for example. However, the way we used to do it is to expand from reference to the sample chamber. That means with fine powders, we have no contaminations in the reference chamber. There are some options, of course, multi-volume and so on. But what we also do, we can, since it's quite small, we can place it into air-free glove box. In some applications, you should not have air or even not even nitrogen. And under, for example, argon atmosphere or something like this, you can simply put this instrument into a glove box. You can easily handle it with manipulators and work. It's also possible to separate upper and lower part. It's temperature controlled via a Peltier temperature unit here. The lower part is the control unit. The upper part is the unit with the sample cell. And as said, it's also possible to separate this. So now I'm coming to another point, which is macro-intrusion porosimetry. This is also one of the methods described in the VDI recommendations for battery characterization. So we use this usually for characterization of battery electrodes and separators, membranes. We do have 2 units. One is a low pressure unit, which can work up to 450 kilopascal, and is also used for the mercury filling of our sample cells. And then we do high pressure units up to 414 megapascal. So we determine with this equipment the pore size and pore volume in the range, pore sizes in the range of 3.6 nanometer up to about 1 millimeter. The measurement is pretty fast, up to about 45 minutes. We can get a complete measurement cycle with all information about the pore size distribution and the pore volume. We can measure up to 20,000 data points. We don't need any gases, no liquid nitrogen, so it simply works out of the box. What is the principle behind? We are dealing with mercury as a non-wetting liquid, and we need pressure to press it into the pores of our systems. So that is one value we get, the pressure. And with this equation from Washburn, we can easily calculate from the pressure the pore radius, knowing the surface tension of mercury and the contact angle, always assuming a cylindrical pore. And another way, it's like a capacitive method. We know also the volume of mercury, which is intruded into the pores. We get then the value of a pore volume. And one example here for an electrode, anodes and cathodes. These were non-calendared, for example. We see here cathode measurements, so anodes measurement with a much higher pore volume in the range of about 320 cubic millimeters per gram, while the cathode had been in the range of about 140. When we have the ratio of the intruded volume over the pore radius, so the dV log over the dr, which is shown here in these peaks, we see that the pore size for both is quite similar in the range of 1 to 2 micrometers. So the pore size is very similar, but the pore volume is different. This is one of the results we get, for example, from this mercury porosity tree. Another example, again, we see here an anode with pore size maxima in the range of about 200 nanometers with the second maximum, and a cathode, for example, in a range of about 500 nanometers. So these are typical results you can get from the mercury intrusion porosimetry. And last but not least, we also have, as I mentioned, it's like a volleyball field. So we need something in the middle. These are the separators or membranes, and even they must be porous. So we do have here an example for a smooth membrane with pore diameters in the range of 10 microns. If it's a folded one, here, for example, we found 20. In another example, we have a separator. So the one is characterized by 3 pore sizes, the range of 90, 50, and 0.1 micrometers. And the blue one here is another separator with pore sizes in the range of 15 to 0.07 micrometers. So you see already that we are covering here the range of, in the micrometer range, a range you cannot determine with the gas adsorption equipment, with the Belsop equipment, but we can easily and very precisely measure with the mercury intrusion porosimetry. And now let me summarize. So some of the challenges and our solutions for the battery materials optimization. We have here first one were graphite and carbons, particle size distribution, and the particle oversize. And so this we did with the particle size analysis with a laser diffraction in combination with an image analysis in situ. So we measured this at the same time on the same material. And the device we used was Sync. Another challenge was a characterization of metal powders, in particular their shape and size. So in particular, shape. And we used here a dynamic image analyzers. So with the CAMsizer X2. Third challenge we faced were solid electrolytes. There was of interest the specific surface area and the pore size and density. So we did gas adsorption analysis with the Belsop Mini X, air protected measurements with special sample cell, or you place the instrument in the glove box. Density measurements can be done with the Bell Techno in the glove box, for example. And these were also the 2 devices we used. And the last one were anodes, cathodes, and separators, the porosity and pore size control. Pore size analysis we did with the mercury intrusion porosimeter using the Belpor LP HP system. Well, and with this, I am already finished. And thank you for your attention.
Thank you very much, Mr. Adolf. So let's check the F&A box. So at the last round of F&As, please type in your questions and then we will answer it. So I give you a moment of time. Let's check. So the first question is, can other glasses also be used to determine density by pygnometer?
What other?
I repeat
gases,
the question.
gases.
Yeah, gases. Sorry. Yes.
Yes. You can do. You can use also argon. You can use nitrogen, except helium. Helium we typically use as the smallest molecule to determine all the pores and if you have very fine powders, but you can also use other gases. Yes.
Okay, thank you very much. Then what kind of infrastructure is necessary for density, gas sorption, and mercury intrusion porosimetry?
Yeah, so for the gas absorption, you need a little bit more. You will need pure gases like nitrogen and helium. In case you know the density of your material, you can even save the helium. You will need, of course, a cryogenic liquid. Typically, we use a liquid nitrogen. For mercury intrusion porosimetry, you will need safe environment. So you would need kind of fume hood where you do all the handling of the mercury, but it's not necessary for the equipment itself. This can be this can stand outside of the fume hood.
Perfect. Thank you very much. Take a look again. So one question, why do we need to know particle size of electrode basic materials?
So it's the density of your electrodes is of course also depending on the particle size. Homogeneous particle size distribution would be helpful for a good say work of your electrodes. In case you will have some oversized grains, they will disturb this. So that's the most important reason is also to know particularly the disturbing particles, so the oversized particles, if you do have them or not. That's a benefit of having, for example, a combination of laser diffraction with image analysis.
So thank you very much. I check the F&A button again, your last chance to type a question. So if you have any questions left, you're free to contact Pautec-Technofarm at nürnbergmesse.de and we will forward it to our speakers. So if no questions are left, I will forward to you some informations. So thanks for joining us at the virtual talk today. Upcoming dates and topics of the next virtual talks and our virtual talks series can you found on our website www.pautec-technofarm.com/events-program or on our social media platform LinkedIn. So stay tuned and feel free to join us again. And we're also very much looking forward to welcome you to Pautec Technofarm, Fachpack and Partec from 23 to 25 September 2025, so next year. So have a nice day, see you soon, and a big thank you to all of our speakers. Have a nice day.